In the middle of the day, the sky darkens. The sun completely disappears, replaced by a ghostly white ring of light. During the night, the moon occasionally enters the Earth's shadow and turns a deep reddish orange. How do the Earth, moon, and sun block each other's light so perfectly to create two radically different visual phenomena? These events are the result of massive shadow plays, dictated by exact three-dimensional geometry. The sun is nearly 1.4 million kilometers wide. The moon is only a fraction of that size. Logically, the moon shouldn't be able to obscure the sun. This diagram shows how we can understand the mechanics using a 1 rupee coin. If that small coin is held close to your eye, it easily blocks your view of a massive distant object like a streetlight. The solar system uses this exact same math. The sun is 400 times wider than the moon, but it also sits exactly 400 times further away from Earth. Because of this exact ratio of scale and distance, the two celestial bodies appear to be the exact same size in our sky, allowing total solar eclipses to happen for observers on Earth. A solar eclipse occurs when the moon passes directly between the sun and the Earth. Because of the orbital positions required, this specific alignment can only happen during a new moon phase. Look closely at the shadow hitting the Earth in this diagram. The dark, narrow inner core is called the umbra. If you are standing inside this specific zone, you will experience a total solar eclipse. Surrounding the umbra is a lighter, wider outer shadow called the penumbra. If you observe the eclipse from within the penumbra, the sun isn't fully blocked. Instead, it looks like a glowing crescent with a bite taken out of it. You must never look at the sun during these events without proper eye protection. The sun emits ultraviolet radiation that causes permanent retinal damage and blindness. To watch safely, you have to use ISO-certified solar filters or eclipse glasses, which are designed to block that harmful radiation. Because the moon's shadow is so small, a solar eclipse is a highly localized event that requires the right scientific tools to experience safely. Now look at the reverse alignment in this diagram. When the Earth moves directly between the sun and the moon, it casts a massive shadow that completely covers the lunar surface. This happens exclusively during a full moon. You might expect the moon to go completely pitch black in the shadow. Instead, it glows red because of how sunlight interacts with the Earth's atmosphere. This is caused by Rayleigh scattering. Rayleigh scattering is a physics principle where particles in the atmosphere filter out shorter wavelengths, like blue light, while letting longer wavelengths pass through. The Earth's atmosphere filters out the blue light from the sun, but bends the red light inward, illuminating the moon. Because the moon does not produce its own light and is only reflecting what hits it, watching a lunar eclipse is completely safe for your eyes without any protective equipment. Solar eclipses cast a narrow shadow and require protective gear. Lunar eclipses cast a massive shadow, turn the moon red, and can be viewed safely by anyone on the night side of the Earth. Since the moon orbits Earth every month, passing through new and full phases, we should theoretically see eclipses every 30 days. In 3 dimensions, we see the actual alignment. The moon's orbit is tilted 5 degrees relative to Earth's path. Because of this, the moon usually passes above or below the direct line between the sun and Earth. Its shadow simply falls into empty space. Eclipses only occur during the specific windows of time when the moon crosses the Earth's orbital plane at the exact same moment all 3 celestial bodies are perfectly aligned. The mechanics are precise. When the moon is in the middle, it casts a narrow shadow on Earth, requiring specialized eye protection for viewers. When the Earth is in the middle, it projects a wide shadow that turns the moon red, visible safely to half the planet at once. Understanding these mechanics turns a rare blackout into a predictable calculation of geometry. You can track these alignments using eclipse calendars or by visiting local observatories to safely engage with the space around us. By mapping these cosmic shadow plays, we turn a temporary moment of darkness into a lifetime of scientific observation.